This video is on the addition to the carbonyl group, i.e. reactions of aldehydes and ketones. Leaving groups tend to be more electronegative than carbon, making carbon more electrophilic and therefore susceptible to nucleophilic attack. Think about an SN2 reaction. So here is ethyl bromide. You know that bromine is more electronegative than carbon. Therefore, when a nucleophile attacks, it attacks the carbon, which is more electrophilic, kicking out the bromide, which was more electronegative. Right? Let's look at carbonyl more closely. Alright, this is a carbon that is partially positively charged, bonded to an oxygen that is much more electronegative and therefore much more negatively charged. If we think about the resonance structure, right, we can actually see that carbon is a very good electrophile in a carbonyl. Therefore, attack on this carbon is very likely. That is literally what this whole next chapter is about. It's reactions on the carbon of the carbonyl. First, we're going to look at the mechanism, and we're going to look at the mechanism under basic conditions and acidic conditions. First, we're going to look at basic conditions. Picture this ketone sitting around and a nucleophile happens to float by. The nucleophile does not have to be charged, it could also be uncharged. Imagine a lone pair. This nucleophile can attack the most electrophilic site, which in this case is the carbon of the carbonyl. This will then form an intermediate anion where we have both the nucleophile and the oxygen still bonded to the system. See, oxygen is the leaving group, but of course it can't leave because it has a double bond to the carbon. Therefore, it only breaks one of the two bonds available. The anion can now pick up a proton from any proton source to give us the alcohol product. Of course, you might be thinking, how can you have an acid under basic conditions? And the answer is you can't. This must be from either water or an acid that is added in a second step. Next, we'll look at the mechanism under acidic conditions. Well, picture a carbonyl. Recall that it should not react under acidic conditions with many things except with the acid itself. So recall that carbonyls do have an oxygen. The oxygen does have lone pairs, so that lone pair can pick up a proton. This is under acidic conditions, so those protons are aplenty. We will then form a protonated carbonyl. Now, you might be thinking, well, why does that matter? Well, let's think about it. We now have positive charge on the oxygen, which, of course, oxygen does not like. So we can show in a resonance structure how that positive charge is shifted. This, of course, makes the carbon way more electrophilic than it was before. So now any nucleophile present, which of course can have a negative charge because we are under acidic conditions, can attack the carbon and yield our addition product. So just to emphasize, protonation of the carbonyl oxygen makes the carbon a stronger electrophile, allowing weaker nucleophiles to attack it. Fantastic.